Good afternoon, respected professors. My name is Yeonjae Oh. Today, I will present my academic background in computer theory, AI convergence research, teaching competence, and my future development plan. My research begins with computer theory, transforms real-world data into meaningful knowledge, and connects that knowledge to AI models that solve practical problems in the real world. This presentation is organized into 4 parts. First, I will explain the fit between the announced field and my academic profile. Second, I will summarize my major research achievements and key papers. Third, I will explain my teaching philosophy and course operation plan. Finally, I will explain how I can contribute to Suncheon National University through industry cooperation, regional innovation, and AI-centered education. This section explains the fit between the announced field and my academic profile. The announced field is computer theory. My research aligns closely with this field because it begins with computer theory and extends to the design of AI models and systems for practical problem solving. Based on theoretical foundations in algorithms, data structures, computational thinking, and knowledge representation, I have conducted research that transforms real-world data into meaningful knowledge and applies it to machine learning, data analysis, and AI-based platform design. Building on this foundation, my research identity can be summarized as AI for real-world problem solving. While computer theory provides the theoretical basis of my research, my work extends that foundation to field problems and actual data. I have applied AI models and data-driven analysis to various domains, including photovoltaic power, virtual power plants, smart grids, smart farms, real estate, and digital healthcare for older adults. Across these fields, my common research goal has been to transform real-world data into meaningful knowledge and to connect that knowledge with AI models and service platforms. This approach demonstrates how computer theory can be extended into practical AI systems, and it can also be directly applied to student-centered education and regional industry collaboration. This section presents my major research achievements and key papers. As the first representative study, I will introduce my work on short-term photovoltaic power forecasting. This study is a clear example of my research identity, transforming real-world data into meaningful knowledge and connecting it to practical AI systems. Since photovoltaic power output changes rapidly when clouds move across the sky, conventional time series models often fail under complex weather conditions. In this study, historical PV power data and sky images were fused through an auto cross-modal correlation attention mechanism. The proposed model achieved strong performance in 15-minute-ahead forecasting, especially under cloudy conditions with large output fluctuations. This research demonstrates how computer theory, data-driven modeling, and field data can be integrated into a practical AI system for real-world energy problem solving. Building on the first study on photovoltaic power forecasting, the second main study expands this research to anomaly detection in virtual power plants. While the first study focused on prediction, this study focuses on real-time monitoring and abnormal pattern detection in complex energy systems. Because virtual power plants integrate diverse distributed energy resources, their operational data are often volatile and complex. To solve this problem, I proposed the MEM-AAE model, which combines an LSTM-based autoencoder, adversarial training, a memory mechanism, and dynamic threshold adjustment. Using real solar power datasets, the model achieved high accuracy and F1 scores, showing strong potential for robust real-time anomaly detection in VPP environments. The third study deals with smart grid stability prediction. Smart grid data are complex, dynamic, and highly time-dependent. This study applied biometric pattern recognition techniques to extract meaningful features from grid data, and then used LSTM networks to model temporal dependencies. By combining the two approaches, the hybrid model enhanced prediction reliability. This study showed how AI can help solve real-world problems. This section explains my teaching philosophy and course operation plan. Although my application domains are diverse, my research methodology remains consistent. First, I identify field problems and user needs. Then, I collect and analyze relevant data, design AI models, and transform the results into practical platforms or services. Finally, I test if they can be used in real situations. This research structure can also be applied to student-centered, project-based learning, where students learn to connect theory, data, AI models, and practical problem-solving. My future research plan is to build an AI platform based on computer theory for local industries. Based on algorithms, data structures, computational thinking, and knowledge representation, I aim to turn regional problems into AI research and education topics. Regional issues in smart agriculture, renewable energy, aging welfare, and real estate safety can be transformed into structured datasets, AI modeling tasks, and practical service platforms. The goal is to build regional datasets, develop reliable AI models, and connect the results to student projects, industry collaboration, and community services. Through this plan, I will extend computer theory into practical AI systems, while also contributing to student-centered education and regional innovation. My teaching philosophy is understand, implement, and apply. Students first understand core concepts through data, real cases, and theoretical foundations. Then, they implement these concepts using Python, AI models, and practical tools. Finally, they apply their results to real-world problems through projects. In computer theory and AI education, my goal is not only to teach formulas and algorithms, but also to help students explain data, understand model decisions, and use AI for practical problem-solving. Based on this teaching philosophy, I can teach courses across 5 categories. These categories are Foundation, Core AI, Data, Convergence, and Capstone. These include computer theory, basic programming, algorithms, data structures, introduction to AI, machine learning, deep learning. I can also teach data analysis, big data processing, time series forecasting, generative AI applications, multimodal AI, and AI service design. In capstone and industry academia courses, I can transform my research experience into student projects with practical outcomes. Through these courses, I want to help students connect computer theory, data, AI models, and real-world applications.
This section is about university contribution.
My industry cooperation plan has 4 steps. The 4 steps are finding local partners, making shared datasets, connecting capstone projects and internships, and sharing the results. I will transform local data from agriculture, renewable energy, welfare, and real estate into education and research resources. Then, I will connect student projects with real company tasks. Through this plan, students can build practical AI skills. At the same time, regional partners can gain practical AI solutions. My goal is to build a long-lasting cooperation model that connects computer theory, AI education, regional data, and local industry innovation. I can contribute to Sun Chun National University through AI education, research, and regional innovation. I will build an AI curriculum that connects computer theory, programming, AI modeling, convergence projects, and student portfolios. This curriculum will help students move from basic understanding to hands-on practice implementation and real-world application. I will also build a regional AI laboratory for solving local problems. This lab will transform local issues into research topics and produce academic papers, patents, capstone projects, and industry-academia collaborations. Through these efforts, I will support the university's global and SW-centered goals by creating a sustainable model for regional AI transformation. My goal is to connect students, research, local industries, and community services into a practical innovation ecosystem. To conclude, my academic direction begins with computer theory and extends to practical AI systems for real-world problem-solving. Through research, education, and industry collaboration, I hope to contribute to Suncheon National University as a faculty member who connects theory, data, AI models, students, and regional innovation. Thank you very much for your attention.